3. So of the 4 lectures I give, oh no, oh no. So we're halfway through lecture 2, but we're now going to do the difficult part of lecture 2. And that means that the 4 lectures I prepared, it may very well be that I only get to the end of lecture 3 in the slot for lecture 4. But let's see how we go. Now, yesterday I had lots of interesting questions and I was grateful for those. And that has led to some additional, what we might call slides, which will be scanned and added to the lecture notes for the eventual post-production on this. And hopefully that will address those questions from yesterday. But I've also had a question which Elizabeth answered in her first lecture, which is who am I and what do I do? And one answer to that is, it's all been such a long time I couldn't possibly tell you. But what I will say is that I moved to Edinburgh about 35 years ago to do a PhD on interactive theorem proving and program verification in type theory, having been energized about type theory at a summer school in 1987. And I'm going to talk about work which I did immediately after my PhD, which was nothing to do with the work of my PhD. And my advice to all students is to guard that time preciously between submission and your viva, because the process of writing a dissertation is subject to all kinds of chemical, physical laws of pressure of a fixed mass inside a decreasing volume. So the temperature and the density of your brain goes up as the pressure of time towards submission presses down on the can of baked beans in your head. And then the moment you submit, the can explodes. And in that explosion, exciting things can happen. So I want to share some excitement from what is now 30 years ago of a formalization of a classical proof of the classical result we talked about yesterday, with some tweaks that were emerging around that time. So we're looking for a relation R that satisfies dP. That's our main idea, because if it contains beta and its transitive closure is contained inside many steps of beta, then we've seen that if R satisfies dP, then our target, namely that this satisfies dP, is satisfied. But I also need some hygiene conditions that R is suitably closed under the term constructors, so it's congruential. And how I'm going to get at this is by a slight device. And the device is to introduce a second relation S, which we can see as a determinization of R. Sam? Very good, very good. Okay, let's see. You have to go back to the beginning, and I hate all this scrolling. dP is the Diamond property. And we're trying to establish it for beta reduction, and indeed for other systems. So the idea is we start with some term M, and consider 2 possible reduction sequences out of it. And the claim is that, in fact, those can eventually be brought back together at a common reduct R. Okay, thanks, Sam. And I'm going to get at it via the mechanism. So I'm going to get at a diamond from a triangle. Okay, so what's the idea? So I'm going to prove a property of the form, let's write M, because that's what I had before. And here's one of my candidate reductions. I'm going to say, if I can establish a relation S, which is like a reduction, and in fact, it's going to be a determinization of the relation R in such a way that if M reduces to P and MS reduces to something else, I can close that triangle with an R step, then I will immediately get the diamond property as a corollary. simply by replaying that game on the other side. And now, unfortunately, I wanted to write R here, but I have R here and here. So let's just put a big bullet for where we want to get to. Okay. So we'll get diamonds from triangles. Oh no, this has gone blank. No, that's fine. Good. Okay. Well, yes.
So this relies on S function, right?
No. Slow down, young man. Slow down, because there's more to my script, right? So here's the triangle property. If I have an S and an R, I can close it with an R. Okay, and I'm going to prove a lemma of the form. Well, I just proved it with a picture, and as we know, pictures contain 87.2 words. I don't require that S be functional, only that it be total. It happens that S will be functional. I hinted that S was a determinization of R.
How do you get the diamond to triangle? You have two different S's.
Oh, because then I have two different S's. So maybe I got the quantification wrong. Okay, I'm going to take an S reduction and consider arbitrary R reductions from the head of that triangle. And whichever one I take, I can close back to this chosen S reduct. So I don't need functionality, but thank you very much for clarifying that, Ohad. But what I did want to say is that we should think of this in the generalized language of relations generalizing functions and all the data being more richly decorated, that we should think of this as a sort of classical decomposition into partial and total correctness. So S is some kind of specification of an operation, and if we can satisfy it, then we know things about the R reducts. So I'll be able to close the diamond, provided I can actually construct T2. So I'm going to have a pi02 statement that says that for any E, there is an S reduct of it, okay? And then I'll use that existential witness to give me that datum, and then I can apply the triangle implies diamond lemma. Okay. Everybody clear on that? Question?
Is the double arrow beta reduction possibly zero step?
Oh, yes. Oh, yes. We built in reflexivity at the ground with variables reduced to variables. And I claimed and offered as an exercise that you prove by induction that it's actually true for all E. But I'll come back to that in a minute, because the other thing I want to say.
Excuse me.
Yes.
On the slide.
Yes.
Around the cross property.
Oh, yes.
The
Dagger.
narrow,
There's no religious affiliation here. It's a dagger.
the narrow that gets a beta after the then, and yes.
Yes.
This arrow that gets a beta on the.
Oh, that I think is you know, mental fluff. That's just habits of mind, writing a double-headed arrow sub beta and then forgetting that it's an R instance of it. But I'm going to claim by further abuse of notation that the fact that R contains single steps and their transitive closure is contained in double-headed arrow beta, that in particular any R step must itself be a beta step, a many, possibly many beta step. So in that sense, that's harmless, but it's clearly an irritating distraction, so I apologize for that. So what are R and S? Now, Tate and Martin Lerf invented a particular R and proved DP for their R directly. And then in the late 80s, Masako Takahashi gave this triangular optimization of the lemma. But already this idea was known in my magical window of 72 to 77 by Peter Welsh in Kent. So he defined a relation R, which we would now call superparallel reduction. It's a bit of a mouthful. Parallel reduction is usually written with the capital R right arrow, double-lined fat arrow, but this is even better, so it's a triple arrow. Okay. He wrote it in ASCII, so it was 3 equals greater than rather than, anyway. And what I'm going to do is consider the S triangular optimization due to, well, Takahashi, but she didn't write it for this relation, but to these subsequent authors following Welsh. So Welsh's tech report, which has languished in obscurity for 45 years, claims that the idea is probably due to the late lamented British computer scientist David Park at Warwick, but also maybe borrows ideas from Peter Axel, the Manchester logician, who followed essentially this schema for general rewriting systems on the basis of which the Dutch school under Jan Willem Klop and his student Femke van Ramstonk sort of codified the idea of super development. So I'm going to synthesize all of this and then retcon history by saying this was known to Welsh, but, you know, bit of latitude here. What are these relations? Well, I need them to be congruential. So I'm going to have x fat arrow x. If the bodies of lambdas fat arrow, then so do the lambdas, and correspondingly for applications. Okay. And then there are going to be 2 more rules, one for R and one for S. And the R rules, I mean, we're going to need to do some beta. So let's do some beta, but let's do a super amount of beta. What does beta say? It says if I already know I have a function and I have its argument, then I can put them together to reduce to the substituted form. And what's super about superparallel reduction is that it does that in both arms of the application. So I'm going to analyze an application, but I don't even have to know I have a function to begin with, as long as I can get one. So if E1 super reduces to lambda E, and the argument A1 reduces to A, then E1 applied to A1 reduces to E with A in the whole. So provided this relation is reflexive, then you can see that this rule will give us an instance of beta. Now, I had the question earlier about possibly 0 steps of beta reduction. Can you all see that from these 3 congruence rules, this relation R is reflexive? Who cannot? Who's uncertain? Who wants to ask me about it afterwards? Yeah, good. Okay, so that's R, and you can actually prove DP directly for R. S takes the same rules, but imposes one additional side condition. So S has this beta rule, but in the application rule, I'm not going to let you get away with not reducing a redex if you create one. Okay, if E1 applied to A1, well, we analyze E1, and if at E2 I get a lambda, then I must apply this rule. Okay, I'm not allowed to give up and just return the application. So I have a side condition that forbids lambdas occurring here. Okay? So I hope it's immediately obvious that S is a subsystem of R. What's surprising is that S is a terminating relation. And this is essentially a generalization of the so-called FD or finite developments lemma to, and then Ohad's question about functionality of S would give us FD bang, the strong form of finite developments. Ohad?
You still haven't defined triple arrow, because you just give us conditions of it, or are you-
No. Sorry. You get so ingrained in habits of thinking that if you write down inference rules, you magically want the audience after 24 hours to know that I mean the least relation such that.
You said if plus.
Heh. Oh, if, sorry. Yeah.
Okay, okay, so it is inductive.
Yeah. So I want these things to be inductive. Yeah. Oh boy. Well. So Elizabeth was very good about identifying what you will know at the end of the lecture course. And I'm much less certain. All I know is that I will have said things, and I hope that you will have heard them. Any more than that is gravy. Of course, I'd like to feel that more will happen, but I'm not in complete control of that. So that's why the questions are helpful. Questions. Now, the grown-ups are asking the questions. Now, that's fine if the rest of you are shy and these guys take the lead. But this is like when I was an undergraduate and the Fields medalists, as they would then become, sat in the front row and dominated the lecturer's attention. It's good, feels nice, close eye contact, lots of attention, but I'm worried about everybody else. So I'm going to take a question from someone else in the room before I come back to Sam's. Kieran.
Sorry, you said that you could prove TP directly from R.
Yeah.
If that's the case, what we've not done, because I thought the proposition that we're trying to prove was that R satisfies.
Yeah.
Blah, 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 blah.
Well, how much work do you want to do in this school?
Not one.
Very good, because in a minute, I'm going to get up here and I'm going to show you how to actually do it in an actual interactive theorem prover. And if you do it by R with R directly, you get one more inductive case to consider. Now, these are systems with only 4 rules, so that's okay. But in general, these definitions might be much more complicated. So anything I can do to reduce an inductive case both increases our understanding of the structures involved, but also reduces the amount of formal work to do when presenting it to the machine. More grown-ups. Your original question. I know, I was hoping you would forget about it. But...
Very simple question.
Yeah.
You said S is terminated,
Yeah.
R is not. That's correct.
Yeah, that's a really good question. In fact, R is terminating. And in a way, you can see that Ohad's original question, is S deterministic? Is it functional? Is a good clue there, because I actually want to not be worried about the nature of that existential quantifier for R. But note this, both the triangle and the diamond from the triangle posits that I already have an R reduct of E. So I don't care whether R is terminating, because my hypotheses are going to offer me, by hypothesis, that R has got somewhere. Okay?
Following from Kieran's question.
Very good.
So if I start adding more cases to my system,
Oh.
what's the effect on the extra cases I get without normalization?
Interesting exercise for the researcher.
Sorry, when you're saying system here, you're meaning the relations R and S.
No, I think I mean Lambda application, okay, products, matching, effects, multiple kinds of terms.
Is that appropriate or the left?
Yes, exactly. They have appropriate laws of lesson. So how many more cases am I actually having when I start scaling up the calculus? Okay, fine.
At least one less.
It could be one less for each S, which is actually quite a lot.
And so R is reflective, that you can show that E is related to R, right?
R is indeed reflexive, but S is not. S is not allowed to be reflexive
Right.
because it has to reduce redexes that are either there at the top level or that are created in the course of reduction.
So this whole exercise was about
Oh.
R not being confident.
No. Good question. The problem is unrestricted beta reduction, which is transitive, is problematic for trying to prove DP. But we're going to get at it by considering a relation R which has DP, whose transitive closure satisfies, contained in beta. And we're going to do that by the strip lemma argument that I showed at the end of yesterday. Does that answer the question?
Excuse me,
Yes?
next previous slide.
Okay.
You say double star is the corresponding termination.
Yep.
How is that termination?
Yeah. So what I'm saying is, and now I am going to borrow OHAD as my stooge to say, is S a function? Suppose S were a function, okay? Then this lemma, if this, then that, supposes that S terminates at E2 and then allows me to conclude something. So it says relative to the specification of S, I can draw conclusions about R, provided E2 exists. So we can think of that as a partial correctness assertion. If the function were to satisfy S and have an answer, then I could draw the conclusions I want. And then the termination argument is to say, but I always can assume that I have such a value. So if we think of S as a relation, as a specification of a function, then the existential statement is saying, well, actually, there really is an answer inside there. So I can always satisfy that specification.
Okay, you don't mean that there is no infinite chain of the DP, so that ESS1, N1 S, E2, E2S, E3, etc. infinity. It's not terminating in this sense.
It's a metaphor.
Just one step.
It is just one step of S,
Okay.
one step of S, and one step of R. And yes, as my colleague points out, it's a metaphor, but it's a metaphor I find useful if we think about the separation of concerns between relational specification and proving things as if we could inhabit the specification, distinct from then showing that there is an implementation of the specification. Because that relativizes the correctness proof to any possible implementation. So we're doing verification without the implementation and then cutting it in at the end to show that there's at least one way to fulfill the spec. And I think of that as termination, but maybe we should think of it as the, maybe better to say soundness and completeness. We would say this is a kind of soundness statement that if the specification holds, then something desirable happens. And then this is saying, but actually we can always ensure the specification holds, considered as a kind of completeness idea. Yeah.
Sorry, it's like confluence. sense of rewriting another way to put this.
It's absolutely another way to put it, and shame on me that I did not say DP is also called confluence. DP is the confluence property.
And because
And again, Latin, that means flows together or flows with. So if we flow apart, then we flow back together.
there's a couple of things that you have to do, isn't it? Like proving joinability and then
I don't know about joinability, but I'm going to show you something that you will then be able to tell us is joinability. That's what I'm hoping. That's what I'm hoping. Because I know you come from a temporary writing background, so you have a different vocabulary and a different armature on which to address these arguments, and I don't have that. So when I get there, maybe you'll be able to tell me. So here's some more blah. S is indeed contained in R because every rule defining S is an R rule. Beta is contained in R by reflexivity, and I've indicated already as an exercise that that's admissible by the usual reasoning. One person asked me about admissibility yesterday. I'll take that question and further discussion of it offline. And I'll just say a bit more about R and S. R allows reduction to proceed as far as creating a redex. Okay? As far as creating a redex. So this thing, as it were, if we applied this rule, would create the redex lambda E applied to A. And R allows us to go one more beta step after that. So R allows reduction to go as far as contracting created redexes. R allows it. But once you've done that, you stop for that redex. But of course, this is happening, very complicatedly inside the term because the congruence rules allow us to do this at every position in the abstract syntax tree. Whereas S, by contrast, forces contraction of those things. So as you reduce by S, you're maybe creating new redexes, and then you have to reduce them. Okay. So this is one slide, and it's about 120 lines of Agda. So I'm going to flip to the Agda in a minute. So termination, as should always be the case in PL and verification, it should be trivial. Things that help make it trivial are if you don't have a complicated Imandra epsilon zero well-founded ordering reducing measure to worry about it, but just by structure on E, okay? There always is a complete superdevelopment of E by induction on E itself. And the only interesting case is if we have an application and then we look at the result of reducing the left-hand side. If it's a lambda, we know we have to reduce. And if it isn't, well, then we know we just get another application term. So that's kind of easy, but important. But we want always termination to be easy because we want the interesting thing in verification to be reasoning with the specification. We want the partial correctness to be straightforward. Now, I don't know whether this is joinability, the triangle property, because what am I going to do? I'm going to go from E1 to E prime, and I'm going to go from E1 to E by R. And this, what's my claim in the triangle property that I can get from E to E prime, so up there, that's, as it were, joining the reduction back to E prime. So is that joinability? Okay, well, let's take that offline. But what's the idea going on? Is that S contracts at least as many redexes as R. So when R happens, there are going to be, as it were, some read X's left over in E, potentially. They might not even be read X's at the top level. They might have been read X's created along the way, so-called residuals of read X's. And so whether this is true or not depends on whether for those leftover read X's, can we contract them all inside one R step to get back to the S result? And the answer is yes. Now, I'll show you this in a minute. So S is a more defined relation, or rather a more strictly rule-bound relation than R. So you should always do induction on the thing which is most strictly defined. So that's S. And then you have an ancillary hypothesis about R. But in all of those rules, the term shape of E1 is determined. And so that will give rise to a possible case analysis on all the R reducts for each choice of E1. Oh, yes.
This case analysis inversion.
So Ohad asks a question containing words which may or may not make sense to anyone. He says, is it case analysis or is it inversion? Now, hands up who doesn't know what inversion of inductive definitions is. Most people. I will show you what it looks like in a language of derivation trees, and then we'll see. But what I'm going to tell you, and everyone else can enjoy the laughter, is that yes, because inversion of inductive definitions is case analysis. Because inductively defined relations are just inductively defined data. And case analysis, or pattern matching on data, is pattern matching on inductively defined relations. And you're shaking your head, and we can go outside and fight now, or we can do it over lunch. Hey? Who's lecturing this? So we do induction on S and case analysis on the possible rules of R. But we need a lemma.
Sorry, are the arrows there for R and S, are they like the transitive versions, or are they just one step?
That's R, that's S.
Yeah.
That's it. One step. But you can go a long way in one step because you're allowed to contract individual redexes that are created. So actually, S will do a huge amount of work because every time it picks up a redex, it's forced to contract it. That will substitute A through the bottom, you know, on and on it goes. Yep. So what do we need to know? Well, this in a sense is the essence of both parallel reduction and superparallel reduction, is that it's a relation which is big enough to absorb reduction inside substitutions. So, good question, Kieran. This is one step of superparallel reduction, and this is one step of superparallel reduction. And superparallel reduction can do enough work that E1 with A1 can get all the way to E2 with A2 in one step of superparallel reduction.
So if you were just using like data and stuff like that, you would need many.
Many. Yeah. And indeed, I wouldn't even know how to count them because it's to do with kind of multiplicities in here, and I don't know how many steps were here. There's some big number involved in this. That's that could be computed, indeed, can be read off from the proof of this, from the number of steps here and the number of steps here. But we're not counting steps because we don't count.
We're just talking about.
No, I haven't finished the point. Hold your horses. So in Imandra, Grant was talking about we have a kind of single axiomatic hammer to hit all termination proofs, which is that we can go down in a very complicated ordinal well-ordering. But one of the great insights of intuitionistic type theory as a framework for specifying inductive definitions and doing proofs by induction is that the trees of definition of the elements of inductively defined data types are self-notating as notation systems for the ordinals associated with the depth of that inductive definition. So structural induction on trees is a way of describing without interpretation the corresponding termination ordering. But that's a sort of secret thing off the side that I didn't want to get into. So there are kind of two approaches to termination. You can either say, give me a big enough ruler and I will promise to step backwards on it until I get to 0. And that ruler, that ordinal, is a straight line. Or I can say, no, let the tree of knowledge blossom as broad and wide and high as it likes, as long as at every leaf of that tree in the sky, I know how to get back to its root. And that's what we're doing with inductive definitions in type theory. And he's shaking his head. This fight is going to be vicious, so start taking bets, kids. So we need another property of relations. And I've rather suggestively written R here, whoops, but this is now hypothetical general R. We say the relation R is substitutive if it has the property we've just seen for superparallel reduction. But I talked about the inventor's paradox yesterday. We're going to talk about the idea of strongly substitutive, which says not just one element, but a whole substitution. And how are we going to R-relate substitutions? Well, I'm going to invent a symbol, square brackets, think lists or vectors. These things are lists or vectors of terms. So I'm going to consider a point-wise extension of the relation, so element-wise. John?
Yeah, when you take a step back, I'm just wondering for the superparallel reduction. Yes, thank you. For the superparallel reductions, you wrote an R with an S over it. Could you?
Yeah. Let's go back. Where did I do that? There or there? That one?
You have like a superparallel, like the 3 arrows, and there was like an R over it.
So, oh yeah, okay. Oh yeah. That's R. That's superparallel reduction, and that's the fat arrow with a D for development. That'll be my relation S. And then I probably, it's mental lint again. I could have written many steps of beta that are R-like. Yes, I didn't need to add, the R is fluff there. That's really just the superparallel relation. And then R is just to emphasize that that's R.
So is the relationship that R is a subset or like somehow included in superparallel reduction, or is it constructed?
No. R is superparallel. And supercomplete development, S, is contained in R, because every S rule is an R rule. So it's a finer relation. Good? And yeah, people write things. You can't type check pencil, thank God, but you're type checking it for me for hygiene and mental well-formedness, and I appreciate that. One reason for the provisionality of marks on paper, partly they're easy to erase, but also I could be a very, very strict constructivist and say, this is noise. The only thing which exists is this. Okay, so let's look at this. Now we're here. No! I'm going to ask you to wait to ask that question, or I'm never even going to get to lecture 3. So by the end of this series of lectures, I have no idea. And you, I have no idea what you will have done. Now, I'm picking on him because he can take it. I'm not going to do that to the rest of you in the room, but I am going to say, for the next school that you go to, against myself, follow him. If you don't know what's going on, or if you think you know something else, keep making objections and slowing me down. His agony out here on stage. This is like open mic night with the worst kind of heckling audience, but it's only one guy, and so far I've got an answer to everything he says, even though he doesn't like the answers. But that means an extra obligation on the rest of you. Yes, here's a question nearly forming. Nearly, yes, nearly.
It's kind of like lattice, basically.
Oh.
You are getting a total, so it's just linear, or it branches out and comes back. So another way of looking at it is like you're trying to prove a partial order like a lattice.
I am indeed for a suitable definition of the operations in a lattice and a suitable definition of the order, showing that we have conditional meets or conditional joins. Absolutely. But notice this, a lattice, everyone knows what a lattice is? Not everyone. Okay, so start off with the easiest example, the natural numbers and their usual less than or equal to ordering. Okay. If I have 2 natural numbers, then they have a number that they are each less than, that is their maximum. And they have a number that they are each greater than, which is their minimum. So there's a very simple relationship between the ordering structure on numbers and 2 operations, max and min, which then have a bunch of properties. You can make it even simpler by having the Booleans, and they form a Boolean algebra, thank God. Other Boolean algebras are available, but the Boolean algebra structure on 0 and 1, with 1 at the top and 0 at the bottom, is also a lattice, and conjunction and disjunction of the associated operations. Now, why am I a little bit nervous to take your cue and say this is like a lattice? In a partial order, there is only one proof that x is less than or equal to y, on at least the classical algebraic account of how this goes. But one thing I've tried to draw attention to is the reason why p is less than or equal to m is actually rich with information, because it's documented all the redexes we contracted. If I just said p is less than or equal to m, and q is less than or equal to m, I'd have lost knowledge of the reductions that took place. And I need to know what reductions took place in order to piece together the common reduct. So actually, your intuition in terms of what the sort of overall structural picture is good. But by taking that big picture, you're losing all the intricate calculation going on inside, which we're now going to exploit. Is that a reasonable?
Yeah.
Everyone's still here. I've got 1 minute left to do the proof. Wow. No wonder lecture 2 took a long time. Somebody asked me yesterday, so I'm going to waste the last minute. Somebody asked me yesterday, why do we need Church-Rosser when more other interesting theorems are available?
You said Who asked this?
No, no, I said someone asked it. I didn't want to identify anyone because it's a very good question. No, it's a very good question. And what I hoped was by taking the simplest, interesting property of the reduction theory of the lambda calculus, it would warm up everyone's minds for the interesting properties I want to get to in the final lecture. But it turns out that this proof from 45 years ago, 47 years ago, is already interesting enough to fill 4 lectures. Well, 3. However, I'll get to it in a second. People who do functional programming, not everyone, it's clear that other programming paradigms are available and have better integration with bounded model checking tools. We usually think of the notion of value as either something we can print, an integer or a string or a Boolean, or a closure, a functional value. And in particular, the thing you can't do is look inside that closure and do any more evaluation. But the general proof of the Church-Rosser theorem is saying if I'm allowed to reduce arbitrarily even inside closures, I can still find common reducts. And that's actually doing a huge amount more work than the sort of vanilla evaluation to values that we see in garden variety FP. Now, we'll see in the final lecture what it is to consider FP-like evaluation as sort of the initial segment of an arbitrary reduction, but in a way that we can then go on to use the structuring ideas that we're seeing here for superparallel to actually build a very fine structure of arbitrary reduction. And before anyone else says, but programs just evaluate to values and we can't look inside them, you just told us that. That's true. But the thing I'm not going to get to now is Morris's 1967 thesis, in which he defines the notion of contextual approximation and contextual simulation. So if we want a real theory of programming that is worth its salt, I don't just want top-level programs and their values to be the things I study. I want to take program fragments and put them inside bigger programs where they use those fragments. And I want a theory of a relation of reduction and comparison between fragments of programs. But now I've got this composite thing of the fragment inside the enclosing context. I can talk about what values that reduces to. And that would have been my 4th lecture, but sadly, there isn't time for that because I've already run over the time for lecture 2. So you'll forgive me if I try and get to the end of it, even though the obvious thing to do is say we've had a lot of blah and pencil. And what I'd like to do is for you to refresh your minds and absorb the beauty of dependently typed programming. But I'm really impatient to get to the interesting stuff. So I'm just going to give you a very whistle-stop tour of what this looks like in a functional language. So we need a substitutivity property. And I've said inventor's paradox that there's a stronger form of it. And here's the inventor's paradox cheap bit, is if you're strongly substitutive, you're substitutive, because single substitutions are substitutions. And then the lemma, or the claim, is that superparallel reduction is strongly substitutive. And I could leave it there because that's the only lemma you need for all this to work. But let's go back and look at those rules. Would anyone like to guess or hypothesize why that might be strongly substitutive? Strongly just says I can substitute with any substitution, not just the singleton substitution of a single term. That's what strongly means. Matthew.
Because anytime there is a substitution for new beta, possible beta redexes, the beta will allow you to carry on normalizing.
That's a good intuition. What I actually want to say, it's our old friend congruence rules, right? Strong substitution more or less says, reduce anywhere in the term structure and reduce anywhere in the terms which you're substituting. But what's the action of substitution? It's just to put all those terms together in a larger composite. And these rules are telling us that we can build up by the term structure of the abstract syntax tree of the term, we can push all those reductions into those trees. So that's the kind of flavor of the intuition. But of course, what am I going to say? This is an inductive definition. So it's true because you prove it by induction. But think for a moment what induction is doing. It'll say, well, I need to consider the case of a variable. How do substitutions act on variables? They substitute for them. I know, it's sort of embarrassingly, I mean, it should raise a laugh because that's all they do. So if I have sigma and sigma prime in this relation, and I pick out an index x to look up in the substitution, and those substitutions in parallel do all this super parallel reduction, then so will their images when I look up at that index. So at the base, I've got the result. And then for the structure, well, I just push everything through the structure. Okay? Because that's the meaning of contextual closure. So what happens in the redex case? Well, I've said that this thing is going to be closed under substitution strongly. This thing is going to be closed under substitution strongly. So I'll look at the image of this term. Well, that's just a substituted term applied to a substituted term. So as long as I can see that thing under the substitution as itself an image under an appropriate, strongly substituted superparallel relation, I'm done. But it's already given to me because the image of this under substitution is just adding A to the substitutions I've already got. And I've said that strong substitutivity is about extending to the pointwise extension of substitutions. So I just add a place in the overall ambient substitution which records this bit of data. And then I'm done. I see one person nodding. That one person can now come down in the self-study period and re-explain that to everybody. I hope you'll take that encouragement, John, either now or at some point in your future career. Okay? There's something subtle about these things, or there's something very stupid and mechanical about it. But in a sense, all I've done is taken beta, that innocent relation, and saturate every position in the abstract syntax tree with the ability to do stuff. And that saturation of the relation then gives me superparallel reduction. And that saturated form of the relation is then something which is strong enough not only to have all these properties, but that saturation is actually where we can mop up those leftovers. And that's probably a very good place to stop. Thanks. Rest, reboot, refresh your minds and lungs with new oxygen, and then we'll come back in 3 minutes.
Well, let's decide what to do. It's now 5 minutes to 12.
Oh my God.
We want to follow the rules, then we'll come back to 20 minutes. Do you want to actually stay longer until our official lunch is 12:30 with audience's interest and James's interest? could, for example, extend the session until 1 o'clock and then have lunch at 1.
How does everyone feel? I'm hot to trot because the coffee's strong here.
How much time do you need for the final bit?
The final bit, haha, I prepared it as a 45-minute lecture, but who the hell knows?
It
Yeah.
looks like it's
So,
very good.
how about we'll have 5-minute break, reconvene at
That's well.
12,
Okay,
and
you two wrestle me off stage at 12:45. If I'm still talking, just
short break.
throw me in the lot.
Yeah, 12:45 left.
Good.
Yeah. Good. Cool. Yeah, we will. Okay, so let's quickly restart with just the tiniest, one shouldn't let too much light in on majesty. On the other hand, this is a summer school, so the whole point is to show light on majesty. And this, from my point of view, is majesty, because someone else has implemented the theory of inductive definitions in which these arguments could be implemented. And therefore, we have an implementation of these ideas in a language which can be checked by a machine. And what do? Well, we write down data types. So I've already made this point about inductively defined relations are just data. So here's some data, and they'll have constructors. And the constructors for this data are, well, I'd rather suggestively use the square brackets as the name of the var constructor, because I want to think of them as looking up in term or in a substitution how to find what happens at index j. And here's the rule that says the variables superparallel reduce to themselves. And here's the rule for lambda. I just go under the lambda and look at the reduction in the body. And this is where we're starting to get the advantage of de Bruijn indexing, is no renaming is required, no pack drill, no rubbish. Okay. Here's application. So I've written it with a fat bullet, so it's a bit more visible. And again, very suggestively, I'm going to say that the proof of a reduction relation, I'm going to give it the same alphabetical prefix as the terms themselves. And I'm going to give it the same constructor name, because I want to think of reduction on terms as on the same footing, or rather, application as a constructor on terms on the same footing as a constructor of proofs of relations. And Agda is beautiful because it allows you to overload constructor names and figure all that disambiguation out. And then here's beta. So E1 reduces to lambda E2, and A1 reduces to A2. And so E1 applied to A2 reduces to, well, square bracket's got a bit overloaded and tired now. So I'll just put the substitution slash with a suggestive 0 to indicate that that's the single substitution that substitutes at position 0. Okay, so that I hope can be read as a version of the beta rule that I gave in pencil. Now, there's some other machinery here, so we want things to be properly scoped, so we need some quantifier prefixes. And there's a bit of notational junk. Brackets say I'm an argument that must be given, and braces are arguments that the machine can figure out, and boy, does that make life easier. Okay, so now let's whiz through some of the easy things that you can do. And there is an idiomatic pattern which is always hard to impress on students, but type theory, because it's not a type inference-driven language, it's a type checking-driven language, you must always announce your intentions before proceeding. So you must declare the type of a function
before you write its body. Okay. And I say function because it's a function, but this is a language in which functions which have interesting types are also proofs of the associated proposition. I've said nothing about propositions as types, and I really don't want to. You'll just have to instead think like computer scientists and just think, ooh, the data language is really weird and rich. That must mean the function language is even weirder and richer. And so it turns out. Okay? So this is a programming language for verification and programming. And here's a program. It takes a lambda term and produces a proof that E superparallel reduces to itself. And what does it do? Well, it does the thing I sketched on the board here. It does the proof by induction. If it's a variable, then it's a variable. So I use the variable rule, and notice that these are the same constructor names and the same constructor applications, but they have different types. So suggestive, confusing, you decide. For lambda, it's lambda, but now it's lambda applied to the proof that the body reduces to itself. And for application, it's the application of the proofs that the two parts reduce to themselves. Okay. And then here's the definition of the square bracket relation, this relation, just as a pointwise extension of this relation. And there's some syntax and some blah there that I won't explain here. But I can immediately conclude that for any sigma substitution pointwise parallel reduces to itself. And it's just the pointwise proof by reflexivity. And then the individual substitution, which I've called sub here, because there's a definition of what zero is, is then the inventor's paradox, cheap conclusion from the harder problem. Now, we want to show the closure of this notion under strong substitutions. Rather, I want to show the strong substitutivity property, so closure under parallel substitution. And I told you yesterday that there was a systematic methodology. You first show it's closed under renamings. And so here's the statement that if two things are in the superparallel relation and I have a renaming, then their renamed terms are in that relation. And that proof is another traversal, and it's a traversal which obeys the same games that we saw in the function definition of the action of renaming. You know, renaming is always with us, but just ride it out. So let's skip over it. Oh, but there's something interesting to say, which is that if you have a beta redex, and now here's the full horror. Here's beta saying, I'm going to give you a beta redex, but I need names for all the arguments, not just the two proofs, but all the terms. What's it going to be? Well, it's going to be some term defined by a lemma, a where clause, which does a bit of rewriting. Trust me, I'm a doctor.
Could I ask you to type text this time so we can get some type?
Oh, yes. I wanted to show you the proofs so that you could have the experience of belief. And then I was going to give you the syntax highlighting so that your belief was confirmed. But if you'd like me to shortcut to just saying, yeah, it's fine.
Just so we can read.
Oh, so it's easier to read. Yeah, so he works in Sweden, so he's very au fait with the syntax highlighting conventions of these things. But like black pencil on paper, I wanted to emphasize just black and white, just provisional. All this extra gravy, which may not even be visible to some of the colorblind people in the room. Green things are constructors, and I'm telling you that that's green. Blue things are defined notions. Black things are variable bindings. And what else do I have? That's it. Keywords. Oh yeah, they're kind of orangey. Yeah. Okay.
Well, the parentheses and like an N of like
It rewrites. Sorry, that's really not meant to be facetious. So here is a term, and it's a term written in mixed-fix notation, but I can tell you that that term built out of those pieces is a proof of an equation. And we rewrite this type with the left, we find the left-hand side of that expression, it's actually here, and we rewrite with it, and that will rewrite in the type of the needed right-hand side of this definition. And then I have two more pieces now, proofs of the right type, which I can put together with beta. So,
in other words, it applies the rule on the left-hand side of the equal sign everywhere it fits inside of the certain right.
thank you.
But not necessarily on the top.
We're still on lecture 2, by the way, trying to get to lecture 3. Ohad.
What you didn't want to say, is on the right hand side, we still have the big, the same constructor beta, is just that we need to get the type of the right now conversion, that's why we're a little bit more messy. A little bit clever, maybe.
So maybe this is my mistake. You shouldn't let too much light in on majesty, because then you also expose the horrible guts beneath. Namely, that if you commit to this way of thinking about organizing your thought in the world, you end up having to worry about equations and equality. Yeah.
And now it imported the binary population, something equals, and that's much difficult.
Yeah, there's a bunch of imports, like really a lot of imports, like really a lot of imports, and like really a lot of imports of the language of the Lambda calculus, and really a lot of machinery that gets renamed in that module importing, and some lemmas I hid from you. But come along now. Come along now. So we've shown closure under renaming, and then there's an interesting little wrinkle here. So if you remember from the definition of the action of substitution, when we go under a binder, we have to lift the substitution. So an important first thing to remember is that parallel reduction also respects lifting. And you need to prove that before you show closure under substitution. But fortunately, because of the definition of lifting, that is simply an application of the proofs and relations version of the map function on vectors. So we have a pointwise relation between vectors, and proofs of that pointwise relation can be thought of as vectors of proofs. So we can map along vectors of proofs if we have corresponding transformations, and the corresponding transformation we use is the proof that they're closed under renaming that we already had in our back pocket from earlier. So now I can get to the statement of strong substitutivity. Okay, so I have a proof E that E1 superparallel reduces to E2, and I have a proof sigma that sigma 1 pointwise superparallel reduces to sigma 2. And now I'm going to show that the action of sigma 1 on E1 superparallel reduces to E2 under that substitution sigma 2. And the proof is the thing I described to you, that because we can go all the way down the abstract syntax tree and everywhere appeal to the pointwise term for term superparallel reduction inside the substitutions, what does the proof look like? Well, it's got, need a bit more. It's got 4 cases because there are 4 rules. In the variable case, the only thing we can do is look up the variables, and sigma is a vector of proofs that says that the substitutions pointwise stand in the superparallel relation. So looking up that vector of proofs at the right point gives me the proof for the lookup of the vector. So there's a huge amount of intricacy going on in the type checking underlying this, which is mercifully hidden from sight. Under a lambda, what happens? Well, I have to substitute in the body, but this is now a proof that E is a proof that the bodies stand in the superparallel relation. And now I'm going to say that that proof can be substituted with a proof about the associated substitutions. And that's going to be the lifting lemma. But suggestively, the form of that function application is intended to mirror the form of that function application, which is intended to mirror the form of that function application. So lambda goes to lambda, and lambda applies to proofs. Similarly, for the congruence rule for application, we just apply in each half and we're done. And then what happens in beta? Well, here's where it gets spelt out. I substitute with sigma 1, a term which is E1 applied to A1, and I end up with sigma 2 acting on E2 with A2 substituted inside it, where all the 1s and 2s stand in the superparallel relation. So what I need to do is somehow get to see that this reduction statement is an instance of beta. And it is modulo a bit more rewriting. Okay. So superparallel reduction is strongly substitutive. And hence, inventor's paradox, it's substitutive. So there's the proof of substitutivity. We just apply the strong substitution property to the boring single vector. Okay, so now here is super development. Well, you've seen these rules before. Oh no, there's an important thing. I needed the side condition that something isn't a lambda. So I'm going to write a Boolean indicator function to test that. And I can do that by structural recursion, few. And then I can write a relation which looks suspiciously like superparallel reduction. And then on pencil on paper, I wrote triple arrow sub D for development. But in the formal development, I wrote triple arrow superscript C for complete super development. So shame on me. I semantically alpha converted the identifiers of the relation names. Sorry, folks, you're used to arbitrary renamings now. So just mentally apply a renaming to everything I've told you in the last 2.5 hours.
So the C super reduction now and no computation of the super.
No, this is just the name of a relation. But what it means is this is the S relation. And the S relation formally is called complete superdevelopment. C for complete. Variables superdevelop to themselves. Lambdas superdevelop to the development of the bodies. Here's application, and here's another clever infix. It's going to look like application. I'm going to supply a term in the middle which says that the expression is not a lambda. Now I wrote that indicator function as a Boolean, and then I'm going to negate it so it's not a lambda. But now I need a type that says that Boolean is not true, is true. The negation is true. So I need an operator called T. We'll talk about that later too. And then the bodies reduce. And under those assumptions, so 2 inductive assumptions and a side condition, then I can reduce the application. And then here's beta, sorry about the wagging finger. So it says, well, now I can just write directly because I'm allowed to write patterns and things. E1 complete develops to a lambda and its arguments reduce. And then given that, then E1 applied to A1 complete develops to this thing, the substituted form. Okay, I said S was contained in R, that's S, that's R, and it's just because every S rule is an R rule, And so that's the proof by induction, and all we do in the application case is throw away the proof, so we don't even need to mention it. And then here's the triangle lemma. What does it say? It says if I superparallel, so this is the R step, but I develop, this is the S step, then I can get from the R reduct E1 all the way to ED, the development of E0. And how do we do it? Well, pattern matching to the rescue again, that does all the case analysis for us. So if I have a variable, I must have a variable, and I use the variable proof. And I don't even need to mention what index I'm doing it at. If I have lambda, then actually I must be reducing to a lambda, because that's the congruential form of the rule. And so it's lambda applied to, well, this proof is what's available by induction. Then if I have a proof for an application that is the application of two proofs, and I have a development proof in the application case, so I know that I don't have a lambda, then I just put the proofs obtained by induction hypothesis together with application. That's one case done. And there's a symmetric case. And so there is something a bit annoying about not being able to eliminate this, that if I'm the other way around where I'm not a lambda, well, then I do the same thing. If I have an application and development forces beta reduction, then I correspondingly force beta reduction. And if I have a beta step and an application step, this is where a bit of magic occurs. By induction hypothesis, so on the left-hand side, RL with DL, I actually have that this must be the reduction to a lambda. So I can pattern match on that and say that must be lambda of something. But because it's lambda of something, I now have a clash with the proof that it's not a lambda of something. So that case just goes away. And then in the beta step with beta step, and I guess this is joinability, now here's where I'm joining two betas. And what do I do? Well, beta tells me that I must have a lambda, so in exactly the same way by induction hypothesis, I must have lambda of a corresponding proof. And that proof, like a term, is a proof with an open position waiting for a proof that its arguments superparallel reduce. So then I appeal to strong substitutivity here to just plug in that proof available by induction. And then that's it. So what does Agda say? Agda says that's 202 lines. Let's not argue between friends. So that's 202 lines of code. 67 years after Schroer wrote a 1,358-page PhD thesis on this theorem. So if nothing else, we have made a tiny amount of progress in the history of thought.
How much would that be in mapping if you write it in a readable mathematical way?
I did it already, but I just left out some details. That's readable math. Your students at a summer school will talk about afterwards what the exercises are to fill in the gaps on the paper.
On 997, you have this jingle jangle that you kind of have to say
that there's a contradiction.
The lambda is a contradiction, right? But instead of having this predicate of like, is it a lambda question mark, returning a bool, you could have a data type constructor, not lambda, which is an empty record for everything that's not a lambda, and a data type with no constructors for everything. And then Actor would not require you to write this lambda. And it would be as proof. Because you still have to import Boolean.
Like the 15 puzzle, moving tiles around with one hole. There's an amount of work to be done
Yes.
and choices of representation about the best way to achieve that. And indeed, other choices are available. Now, I haven't done this experiment before, hold on. But there's an even shorter proof, which is to comment out that case, because that is a case that can never happen. And pray to the gods of type checking that the type checker is smart enough to know this. Oh.
But it would be smart enough to know it if you had void for the false.
No, I do. There's void there. That says this is, I have an impossibility generated by the clauses.
Question mark Lambda.
But true of false is empty on the representation I have. But sadly, it's not quite smart enough. And so tails between our legs, we withdraw and say, for the sake of understanding, we have to remind ourselves that there is no work to do. And then we're done. Oh no, we're not done, because that's just partial correctness. Oh, it's all such hard work doing PLM verification, because you have to prove partial correctness and then you have to show total correctness. So you have to show that there exists a complete superdevelopment. And what is existence? Well, it's to give the term together with the proof that they stand in the S relation. So proofs of this are going to be pairs consisting of a term and a proof. And the proofs attractively look like what you think they should. Variables are just variables paired with the variable proof. Lambdas are just lambdas paired with the lambda proof, provided we have the decomposition for the bodies. And then I said you have to do case analysis in the application case. So here it is. I get a term which is the super complete development of E and a proof that it is indeed such. And I also have the corresponding thing for the argument. And then this is where it is a bit crunchy. I have to do something in the lambda case, and what I do in the lambda case is beta reduce. So I have the beta proof and the substituted term as the reduct. But then I actually need cases for all the others. I can't just wildcard match that, because the type checker isn't quite smart enough to recognize that both of those proofs would have the corresponding appropriate type. So I have to do a little bit more work. And then here's the proof that triangle implies DP. So that's the statement, and the proof is pretty much as short as the statement. And I won't say any more about that. And then we're done. So now I've used half of lecture 4 to finish lecture 2. So buckle up, everyone. It's going to get busy. Here's lecture 3. And I'm just going to be very, very, very hand-wavy about this. Oh, no. Church Ross is easy. We can do it in 200 lines. Standardization is more interesting. It takes about 400 lines. But a lot of that is boilerplate, and we've seen a lot of boilerplate. I have to show things closed under renaming. I have to show things closed under substitution. I'll circulate the AGDA later. But what is it? So this is a proof. Sorry, this is a statement of a thing which appears in about chapter 9 of Curry and Faze's book on combinatory logic under the immensely memorable name of property D. And there's a complicated proof of property D that in the language of the time is written out in English with almost no symbols. So an instructive exercise in embracing the past is to learn to read medieval manuscripts. And when you read Curry, you are in the presence of medieval philosophy. Latin and all. So that's what they did in the late 50s. And then there's a very interesting history to proofs of this theorem, because it should have been immediately understood as provable in 1958 for lambda calculus. And indeed, it was known in my golden period of 72 to 77 by the lambda calculus experts in Oxford, Utrecht, Stanford, and Paris, by a very complicated annotation system on terms, so-called labeled lambda calculus. The actual proof that you cite if you want a citation for standardization for the lambda calculus is actually a proof that comes after that in 1979. Unfortunately, it had already been proved by Gordon Plotkin in 1975 for the call by value lambda calculus in a paper suggestively titled Call by Name, Call by Value, and the Lambda Calculus. And I think after he does it for call by value, he then basically repeats it in a paragraph for call by name. And we're going to look at the call by name version. So this is a theorem that already had a proof before the proof of it was published. Let historians argue. But let's say this. I said at the beginning that one of the things about the medieval literature of this topic, even in 90 years, is that people introduced all kinds of additional armature of reasoning on top of the terms themselves. And what I've tried to emphasize for you going forward is to take that armature away and reason directly with the relations as you might define them. So labeling of lambda terms is a way of marking which redexes I'm allowed to contract. And when I contract them, the label goes away, or the label gets smaller if I want to go down in some very Baroque ordinal analysis. But we don't need that labeling. Plotkin did it, computer scientist working in the 1970s on lambda calculus. What is the one data structure you have access to? We've already seen it a million times in so far. You have the list. So he writes a proof based on lists of terms which witness the reductions. And he proves a lemma about how you can concatenate those lists and how you have to permute between them. So-called standard sequences. Now, what is a list? It's but the fringe of a derivation tree involving all the subterms standing in the appropriate relation. So I'm going to write derivation trees, and you can read off his sequences from those. And in the 15 minutes that remain, I have time only to tell you what the statement is and to sprinkle a little insight into why it might be true. And the insight is why Michka's 1979 paper is important, because it isolates a key abstraction, the idea of semi-standardization, which I'll say what that is in a minute. And because we now, in 2022, live in a world of such beautifully rich inductive definitions, the property of reduction sequences that Michka established, I can now make a definition. And having made it a definition, if I then make that definition mutually with all the rest of the armature of derivation trees, magically the proof falls out. Well, what is standardization? And this is what you get if you look in chapter 11 of this book. So somebody said, where can I read about the things you've been talking about? Chapter 1 of this book, the overview introduction to this book. Chapter 3 of this book does the parallel reduction proof of Church-Rosser. And chapter 11 states and proves standardization. And this is the statement of standardization. And you can kind of understand why, even if you can prove it, you might think, why do I care? What? It's even the case that in the original, there are 2 levels of qualifying parentheses qualifying this definition. And what it essentially represents is a kind of spatial invariant on the positions in a term at which reduction takes place. And what it formalizes is the idea that reduction proceeds from left to right. But understanding what left to right means this if you are writing in 1977, 1984, or the revised edition in 2012. I think we can do better. And this is basically Plotkin, but dressed up in the language of derivation trees. I said we live in a magisterial kingdom now where many things are possible. And in particular, I can define 2 relations at once in such a way that they depend on one another. Now, what I will define is a notion of standard reduction, double arrow sub S, and internal reduction, double arrow sub I, mutually. And about the only thing I can tell you is that the definition of standard reduction is Michka's semi-standardization property, namely that a standard reduction is a weak head reduction prefix, and we'll go back to that in a minute, followed by an internal reduction. And then internal reduction is pretty much what you think it should be. It's where you reduce internally. So variables reduce internally to themselves because they ain't got no structure. So that's all they can do. Internally to a lambda, I reduce to a lambda, but I can restart the process by standard reducing the body. So this kind of hereditary property, where each time I go under a term constructor in internal reduction, I restart standard reduction, is how we're going to establish the spatial invariant that the redexes all move from left to right. So what happens in application? Well, applications reduce to applications, and the arguments, and I must apologize, I've alpha converted again. I had E and A and it was all very beautiful. And then somehow combinatory logic took over my mind and everything is capital M and capital N again. Sorry. The arguments, we restart with a standard reduction, but the function position, the left-hand side of an application, I'm only allowed to do internal reduction. So hopefully, given the last lecture, we can immediately see that this relation, I, never creates a redex at the top level. Oh, that's not quite right. No, it is. It can create it, but it can't contract the ones it creates because they'll just stay stuck here. Okay. Now, what's weak head reduction? Oh, man. Oh, man. Oh, no. Oh. Sorry. Oh, yes. Oh. It was tacked on the end. Oh. Weak head reduction is how Haskell executes. In an application, I see if I can get a function, and if I get a function, then I apply it to its argument. It's called by name. So it's defined, or a possible representation of its definition. Other representations are available, but they're all equivalent. Have I finished the definition and then another question? Okay, so if I beta reduce at the top level, then I'm definitely weak head reducing. Okay, so top level function applications, yep, that's a weak head reduction. But otherwise, all I can do is reduce in the function position, and the argument stays the same. So in particular, functions, lambdas, not only cannot reduce, well, they cannot reduce. If I have an instance of this relation, then E prime is equal to lambda E, but also no read X's were contracted. And correspondingly, if X reduces to E prime, then E prime was X and no reduction took place. So we say that those two things are weak head normal forms. And then E applied to A, what can we say about that? When does reduction happen? Well, reduction will happen if E eventually creates a lambda. And if it can't do that, then we have a weak head normal form. So I'm just very quickly going to describe normal forms. So we have more inductive definitions. You can detect my vibe here, right? So let's look at really terms in which no reduction at all can happen. Variables. Lambdas, if no reduction can happen at all in their bodies, and applications, provided E is normal and A is normal and E is not a function. So those are the normal terms. Those are the gold standard of, no, I'm done. I've really finished. No more reduction available. But, you know, people can't help wanting to redefine things and have equivalent representations. And there's at least two people in the audience who may be interested in this. We can factorize this rule system in order to eliminate this annoying negative side condition in favor of a pattern match as follows. We can define two notions of normal form. It's like Sith laws, always there are two, the neutrals and the normals. So the normals drive everything. Lambdas are normal if their bodies are normal. But expressions can be normal if also they're neutral. What are neutral terms? Well, variables are neutral because they can't do anything. They're just waiting for substitution to happen. That's all a variable can do. And an application is neutral, and you should think computationally as a neutral term is somehow stuck. Can't do anything yet. But it may do if its variables get instantiated by an ambient substitution. So an application EA is neutral if E is neutral, so there's the inductive thing, and its argument is normal. So there's nothing more to do there. So that's another mutual definition, like standard and internal. And there's a corresponding one for weak head normal. Well, poor old variables, they really can't do much in this game. So they're weak head normal, and lambdas are weak head normal. I said that. And then E applied to A is weak head normal. If E is weak head normal, can't do any top level reduction modulo a spine of applications, as long as it's not a lambda. But look now, there's that horrible side condition, E is not a lambda, and I said we can fix that by doing a mutual definition. So alternatively, student exercise, write down the definition of weakly neutral and weakly normal and make them play off each other. Oh, the Y combinator. No. So now what's going on? What we're going to show is that an arbitrary beta sequence gives rise to one of these. And what are we going to do? Well, we need to find where all the reduction happens and somehow organize it so that we do a bunch of these outermost Haskell evaluations and then a bunch of structure preserving inner reductions. And I'm just going to tell you we can. Oh no, I've got 7 minutes. I can almost tell you more about it. No, what's the question? That is a defining clause. It's a relation defined inductively by one rule, but it's defined mutually with a relation which depends on S. So actually the whole thing is, the box is just to draw attention to, this is the most important thing to understand about standardization, is the semi-standardization. But this also draws attention to the thing that I said about reduction inside a context, is that's Haskell reduction, but we can play this game for call by value. Gordon already did it 40 years ago, 50 years ago. But the point is, if we consider contextual reduction, we might actually need also to consider these bits. So actually reducing inside expressions to understand their behavior in arbitrary contexts may become necessary. Now, but the other reason for putting a box in is because it's a single defining rule. But it's also that thing that I've taken what was previously understood as a property and now making it definitional. So I've cheated. So Russell always referred to hypothetical reasoning as the advantage of theft over honest toil. Turning a property into a definition plays the same role. You pay in the end, but you pay by establishing that this definition and its friend internal reduction can be put together. Have I lost you?
Well, what I want to ask a question.
Good. Yeah.
So, no, just wanted to ask, was the LSM to generalize this theorem? Because it seems that.
Sorry. Did what generalize what?
This theorem. Because it seems that it highly depends on concrete rules. Meaning that if one more rules is valid, it's really like broken.
Oh. That is a very profound question, which goes back to this magic shibboleth that I used of admissibility. The properties of rule systems are extremely sensitive to the choice of rules. So your mileage may vary if you change the language. But one reason for the organization of the proof that I would have shown you is that it is intended to be robust to extension by new language constructs, because there's a systematic way in which you can understand how to either extend the evaluation language of weak head reduction or the language of internal reduction in such a way as to preserve this factorization. But indeed, the margin of this letter is too small for me to give you the details of that construction. But no, that's an extremely good question. And I've been very fast and loose saying, rules, here we are, it's all fine and lovely. But rules are a presentation of a concept, and therefore you have to kind of mind your P's and Q's as well as your M's and M's. Question. He's going to wrestle me off stage. I'm going to have to stop. I've got 3 minutes and 2 seconds. We are.
It's essentially a partial evaluator, for example. In terms of programming language interpretation.
Stand up, Dr. Sam Lindley of the University of Edinburgh, a doyen of partial evaluation, normalization by evaluation, and many arcane secrets. And I will let him answer that question for you, and I will just draw in a lot of oxygen, puff up like a blowfish, in response to the stress of the question.
You want me to answer it now?
No, I forbid you to answer it now. But I wanted to make the binding between people who are interested in the answers to that question and the man who can answer them. But I want to get to one more thing, and then I'll take those questions. So first of all, here's a slide that just says, but you can just ignore it. That spatial metaphor, property dagger, that was written with the depth 2 of nested parentheses, and spatial intuition about redex occurrences and residuals, I haven't even told you what residuals are, you don't want to know, is actually something which can be read off inductively from this definition. So we haven't kind of done violence to the concept, except in one part. So when I wrote this, I bet you're all sequential imperative programmers at heart instead of parallel functional programmers. Because I bet you when you saw that rule, you thought, first I reduce n, and then I reduce n, and then I can conclude. But derivation trees are magical mobiles, and we can permute the premises when they're independent. And if we permute the premises of those rules, then we violate the spatial invariant. So if we really want Plotkin's construction, we need to be sharper still and say, first we do the left, and then we do the right. So we need three relations, left internal, right internal, and internal. And those poor variables, all they can do is reduce to themselves internally. Otherwise, an internal reduction is a left internal followed by a right internal. So I've sequentialized the derivation tree, permutation invariance, parallelism. Oh, and I've left out Lambda as well, poor old Lambda. Oh well. Application is the only place where anything interesting happens. To do a right internal reduction is what? Well, it's to do reduction on the right. But we saw already in the definition of internal reduction that the argument is allowed to standard reduce. So that's that rule. And then the inductive invariant of internal reduction is that the function position must be internal. So that's that rule for left. So I'm proliferating definitions, but they're very simple because these two only have one defining rule. And then internal reduction is just organizing that. So if you want to be really, really precise about the standardization theorem, you want these definitions. And these do satisfy invariant property dagger. And now I will just silently withdraw, leaving the leaves that have now fallen off the tree at the end of Waiting for Godot, with this last slide, which is the proof of standardization, which is, we look at it. A beta step is a weak head reduction step, and internal reduction is reflexive. So we're done. Variables, poor old variables, they can't do that. But that's okay. They don't need to do that. Lambdas do lambdas by going under the constructor. And in applications, what do we do? Well, there was an earlier argument which will be in the slides that shows why it's closed under application. So these relations form a congruence. Well, they're contextually closed. To form a precongruence, we need them to be transitive. And I said right at the beginning, transitivity is the hell of inference rules from which you must do your utmost to escape. And what is the transitivity of standard reduction? It is this picture. If you factorize into weak head reduction followed by internal reduction, transitivity says that we can appropriately close this triangle by filling in that dial. And so given the mutual setup, what it corresponds to is simultaneously showing transitivity for S, transitivity for I, and then the most important thing, which is that if I do internal reduction and then Haskell evaluation, I can drag all of that Haskell evaluation to the front. And the reason I can do that is because internal reduction preserves the property of being a redox and preserves the reducts of the associated reduxes, because it doesn't change the term shape, because all the reduction is internal. And that starred property, the permutation property of I and W, is the heart of semi-standardization and hence standardization. And it rests on many steps of W. So it suffices to consider one step of W plus some congruence closure, but that's okay because all the reduction happens on the left in W. So all we have to show is that we can drag one beta step through internal reduction. And then with no minutes to spare, the caterer's angry, everyone going hungry, I will just say what? So there is a formalized proof of standardization. And I'll get there. I should have had this set up earlier, sorry. Got to go a long way, you see. Long way. Where's beta? Where's I star beta? Oh, come on. That's standardization of one step of beta. And you scratch your head and you think, oh, property D. Oh, how is it proved? It is proved by pattern matching. There is only one possible form of this composition of reduction, and its pieces can be put together to make a standard reduction. And with that, we are done. There's a postscript. The credits have been rolling, lunch is happening, and then Thor appears. Says, yes, it's actually true because it typed it.
All right, questions over lunch. Lunch at that time. Yes.
So that's doing after lunch before the next match. And then on the topic of last chances, we will have a photo after ground password software. Today is the only day when all speakers are in the same place. So
Fantastic.
please come at 4 o'clock for a photo.
Yep. We don't. Okay.